Good morning, everyone. My name is Rafael Copstein, and I'm here to present a paper entitled Log Abstraction from Information Security, Heuristics, and Reproducibility. So when we look at information security and in network operations, we have nowadays very big networks that are composed of many systems and services that have to interoperate to achieve our objectives. And we can see them as very heterogeneous networks because all of these services come from different sources and they have different ideas. And when it comes to log analysis, we have to group all of those logs into a single source. We have to gather all of them so that we can do further analysis. And from a perspective of security, this leads to very complex alerting scenarios because attacks and malicious activities can come from any of these services or even from them together. And even though we have very good solutions for log collection, we have a lack of security-centered solutions, which would mean that they wouldn't take into consideration the combination of all these logs, but provide more regular interfaces for analysis, such as dashboards and text-based search. So our objective with this research is to provide a holistic insight into threats and malicious activities by way of forensic incident analysis and log pools. In other words, we want to collect all of these logs from these multiple systems and be able to tell when a specific threat or malicious activity is going on, even if it is composed of multiple surfaces at the same time. In this paper in particular, we looked at the current state of the art for algorithms on log parsing and abstraction, and more than that, we looked at how they would fare in specific scenarios of security analysis. So here's an example of what one of those algorithms would do. So given the 4 lines of logs that we have, for example, they would look at those lines, find similar ones, and group them into sets that are represented by templates. So in our example here, all of the log lines that talk about a specific user logging into a machine are grouped with template 1, and all of the messages that talk about a software being crashed are logged into template 2. These templates are composed of both static words and wildcards, as in the asterisks, that could mean one or multiple words, but the idea really is that they are the variable values of these logs, so the variable ones on these templates. So to start looking into those algorithms, we reached for a paper named Tools and Benchmarks for Automated Log Parsing, which was published in 2019. And it is a literature review of many of these algorithms for log parsing and log abstraction that also includes experiments to measure their performance. And what was interesting about it is that they also made everything available open source, so both their implementations as well as the data sets they used for evaluation. So we decided to start by re-executing those experiments and seeing how much of the published performance that they've given was in fact achievable by us. So we ran that experiment, and although most of the results were very similar, we did find a couple of things that struck us as a little odd, such as in the scenario where we're running the log-sig algorithm over the Android dataset. We just couldn't get a result because the execution would not finish in a reasonable amount of time, at least when compared to the other executions. And also, as you can see in the table, all of the highlighted cells were situations where we got a result that differed from the original by at least 10 percentage points. And that's kind of striking because most of these algorithms are deterministic. So we wouldn't expect to see that amount of difference from the original ones. So we came to the conclusion that this makes them a little less robust in terms of getting consistent results throughout multiple runs. So we had this idea of the performance in terms of accuracy over an annotated data set, just like the literature review had. But when we look at it from a perspective of information security, we really can't always assume that we know what our objective is, what is that we're trying to find. We're trying to find anomalies, we're trying to find security breaches, but we can't always assume that we have a ground truth for that. So when we look at conventional performance metrics, we are really depending on a previous annotation and a previous definition of what those threats and malicious activities are. So instead of relying on that, we decided to try to go again into this idea of the holistic view to be able to see this from the perspective of multiple systems. So we came up with this measure of the ability to abstract. We're trying to describe the performance of the algorithm without relying on an annotated data set or without relying on data that has a particular solution to. So the idea of the ability to abstract goes as follows. We have 3 data sets. So the first one is the homogeneous data set that's composed of logs from an Apache web server, we have the heterogeneous data set where we include logs from a system that's running multiple services, in this case, Linux system logs running multiple applications on top of it. And finally, we have the mixed service data set. There is a combination of multiple logs, in this case, HTTP, SSH, DNS, FTP, and SMTP, combined together, mixed together into a single set of logs. And we measure the ability to abstract by getting the number of groups that is resulted by each one of those algorithms, and we divide that by the maximum number of groups that that data set could possibly yield. And that number is just the total number of lines that the data set has. If we assume that every single line is totally different from every other line, we would have as many groups as we have lines, hence the maximum number of groups that we could have. So ability to abstract is this ratio. And when we ran the experiment, these are the results that we got. And they describe how much the log was able, how much smaller the algorithm made that original data set, how compressed that became in terms of groups and the templates for each of the log lines. But again, since we didn't have, we didn't want to rely on any sort of ground truth or correct answer, we needed to find something that we could describe with these results. And that's when we stumbled upon the idea of the 50% rule. So the 50% rule says that the number of groups, if the number of groups yielded by an algorithm is higher than half of the original number of lines that the dataset had, then at least one of the groups is composed of a single line. And because that group is composed of a single line, we argued that that algorithm was not good enough to find the similarity between that line and the other lines in the dataset, and therefore it's not able to abstract these datasets enough. So just 6 algorithms out of the total were able to respect this 50% rule throughout the datasets that we proposed, those being AL, Drain, LFA, Log Cluster, Shiso, and Spell. In the specific case of Log Cluster, we saw kind of the opposite effect, where Log Cluster was grouping every single line into a single group, which means it was able to find similarities between all of the lines, but it was not able to find any dissimilarities. And again, we argue that this is almost as bad as not finding the similarities between the lines, because they are in fact different. So what these algorithms must be able to find that level of dissimilarity as well. So talking a little bit about interpretability, interpretability is very important in the field of security, because we always want to have a reasoning why we made a choice. We can't just let the algorithms make the choices for us, because we want to go on to find why such a problem was caused. We want to be able to send the right teams to deal with first response actions, especially in the case of an enterprise. So we really need this explainability. We need to be able to say why something was categorized as a threat or as a malicious activity. And currently, we don't believe that log parsing and log abstraction algorithms are able to do that. And that's why we introduce the ideas of heuristics, which is to be able to look at either a log line or a template that was generated for one of the groups and be able to say what was the driving idea, what was the driving heuristic when grouping that specific log or grouping that, generating that template for that specific group. So we thought about 3 main heuristics, being the time, actor, and protocol. And the way we measure this, the way we find out which heuristic drove a specific group is using an algorithm that tries to mimic a human expert, in the sense that it looks at every single word and tries to associate each of the words with one of these heuristics. The one heuristic that has the most words associated to them gets to be the heuristic associated with the group itself. So in the example here, we would have 1 token that's related to time, we would have 2 tokens that are related to actor, and 1 token related to protocol. So overall, we would categorize this line as following the actor heuristic. And we used this in the results that we obtained in our first experiment for measuring the ability to abstract. And we found some interesting results in the form of the AL algorithm over the heterogeneous data set, where every single one of the groups was categorized under the time heuristic. And also the same thing for LFA, again, on the heterogeneous data set. But we can see that that's not a recurring pattern, because when we look at other instances of those same algorithms being run on different data sets, we see that it's not always the case that time is used as a heuristic to make those groups, to generate those templates. And also other algorithms did not find similar ideas as always following the same heuristic. They have much more distributed numbers over all those heuristics. So thinking of that, we decided, okay, maybe what if we change the data set? Maybe that is something that's influencing those results. We want to see how those algorithms fare on different log sets, on different applications. And that was when we compiled more data sets with more applications that could be running on an enterprise, such as Apache, firewalls, operating systems, IDSs, and so on. And we replayed that experiment over these logs. And what we did find was that there was a strong relation between which data set was being evaluated and what heuristic was being used by the algorithm. So there is no correlation to be observed between the algorithm itself and heuristics, but much more between the data set and the heuristics. So the results of the algorithms are not consistent in terms of heuristics, which would be something desirable from the perspective of explainability. So knowing these, reaching these conclusions throughout our analysis, we suggest a couple of metrics that any algorithm trying to work with security logs or security data should follow. And the first one would be the ability to abstract. So any algorithm should be able to respect that 50% line in a similar scenario as the one we tested, so that we can argue that it's able to see a reasonable amount of similarity and dissimilarity on those logs. We also suggest the ability to handle heterogeneity, which would mean that that algorithm is able to produce groups in its majority using the same heuristic. So it's very consistent with what heuristic it uses. And finally, the ability to describe using heuristic would be the ability to produce groups that are never associated with an undefined heuristic. So even if not always the same, at least the algorithm is following one of the heuristics every time it generates a group. So out of the 5 algorithms that we deemed able to abstract, that we found that respect the 50% line, we did not find any that do respect the ability to handle heterogeneity or the ability to describe using heuristics, which leads us to believe that the current state of the art for log parsing and abstraction is not yet ready to handle problems centered around security, and especially heterogeneous security. So in conclusion, we don't see a holistic view in the current state of the art for log parsing and abstraction. So we don't see these algorithms being able to see all of these multiple sources and find threats and vulnerabilities and security problems in general. We also conclude that the conventional performance metrics are not sufficient to describe your ability to handle problems in security, because all of these algorithms are the state of the art. They're the ones that have the best performance, but that did not translate into them being able to handle these problems that we analyzed. And we also, as a contribution to the area, we introduced this idea of looking at heuristics being used for grouping these logs. To the best of our knowledge, this is the first time that heuristics are being used for this scenario. And we also contribute by introducing those 3 metrics for security in the ability to abstract, the ability to describe using heuristics, and the ability to handle heterogeneity. So as our future work, we would like to see those algorithms improved. We would like to be able to provide them with those abilities that we proposed. We would like to be able to see more than one heuristic being applied to each one of those groups in scenarios where we might have a tie, for example, or a group that is in fact grouped by 2 different categories, like time and actor at the same time. We would like to be able to see that and explore that a bit further. We would also like to look at the idea of undefined heuristics and really understand what makes for an undefined heuristic. When can we really claim that something was not grouped by any heuristic at all? We would like to apply these experiments to alternative log files, to different applications, and seeing if maybe a different structure or a different application creates different results in these experiments. And finally, we would like to come up with new security metrics for this area, or even see new ones in the literature and be able to explore them in our own work. So thank you very much for listening. Again, my name is Rafael Copstein, and I would just like to acknowledge the support of Dalhousie University, the NIMS Lab, and CERC, 2 keys, and the Government of Nova Scotia in Canada. for their continued support, and I will now take your questions. Thank you very much.